Welcome back. I hope you already know the use case we are working on. If not, please check the first movie explaining the problem we are trying to solve. In this movie, we'll cover the first two steps from the pipeline, unifying and cleaning, and converting to RDF. Both of the steps will be performed in Google Refine, but before we start using it, it's worth mentioning a few words about its capabilities and functionality. Google Refine is a powerful tool that can be used for cleaning up raw data and linking data to registries, such as, for example, Freebase. It can be used to help identifying duplicates, discovering patterns in data, and spotting inconsistencies in uploaded data. Very good tutorials about general capabilities of Google Refine were provided by creators of the tool and are mentioned below in the description of the movie. In order to have our data processed in RDF form, we'll have to use RDF extension to Google Refine. RDF extension to Google Refine can reconcile strings such as the name of the borough to any database identifiers. This provides a straightforward way to create explicit links from ambiguous strings to existing entities provided by any Sparkle endpoint or RDF dump. Moreover, the extension can express these connections in RDF. All of these features are supported by a friendly graphical interface. We assume that you have Google Refine already installed and RDF extension to Google Refine downloaded and unzipped on your hard disk. We provided proper links to download pages in the description of the movie. The installation of the extension is pretty simple. You just have to place downloaded archive into the extensions folder located for Mac users in Library Application Support Google Refine Extensions. If such folder doesn't exist, please create one. This way, RDF extension to Google Refine should already be added to Google Refine. You should see a small RDF button in the upper right corner when opening or creating a new project. Before we import our data, we just want to mention what kind of formats Google Refine currently support. We can import data separated by separator, such as TSV, CSV, and custom separator, Excel or Google spreadsheets, XML data, RDF data in the form of XML or N-triples, but also JSON format. The data we decided to upload are Excel sheets from London Data Gov UK. We downloaded 3 datasets, but we'll be working in this tutorial only on one of them, borough profiles. The other 2 datasets, energy consumption in boroughs and police records in boroughs, are processed in a similar way, thus we'll leave them for you as a practice task. If by any chance you get lost, we provided individual Google Refine projects to download in the movie description. In the first phase, we'll focus on unifying and cleaning our data in Google Refine. To do so, open Google Refine if you still haven't done that and click on Create Projects. Choose Borough Profiles file and click Next button. We see that we can import 3 different worksheets, profiles, lookup, and data. Since we want to work on raw data about London boroughs, we select the data box. Now we can see the preview of the data that will be created. We can see that at the bottom of the page there are also some other options which could be applied to initial cleaning of the data from unneeded rows or cells. As we see, our worksheet contains empty rows and cells, so in order to get rid of them, we simply have to unselect the following 2 options: Store blank rows and Store blank cells as nulls. We can't do much more here, and these are the data that we really want to work with, so we just have to click Create Project. Initially, we see only 10 rows, so first we extend the view to see the whole set. When we scroll down, we can see that there are some metadata. Since we want to work on raw data about London boroughs, so the first thing we'll do now is to get rid of those metadata. In order to do so, we just have to mark with stars all rows which we want to remove. We'll also remove the information about inner and outer London and some general information about England and country, because we want to work only with London boroughs. When all of the rows we want to remove are marked, we just have to click on All, then Facet, and finally choose Facet by star. This way we filtered our dataset. In order to remove unneeded rows, we click on True in the Start Rows window. This way we see only these rows which we are going to remove. Removing process is pretty easy. We just have to choose Remove all matching rows from All Edit Rows. Now click on False in the start rows and you will see the dataset without the metadata. Now, let's look at our data. There are many columns that probably are not so important from a real estate business point of view. For example, male employment or female employment are not the information that potential buyer is looking for. Since we won't need all data from this file, we can either remove them or build a skeleton in the next phase just on the part of the columns. However, it's easier to work with the table with less columns, that's why we decided to remove some of them. Removing is very easy. You just have to click on that small triangle in a column we want to remove, click on Edit Column, and then remove the column. We decided to remove around 36 columns, but as we said, this was done only for clarity of the dataset. If you want to include them in the future skeleton, these data won't appear there anyway. So now our dataset is cleaned from metadata and unneeded columns. The only thing that could be improved is removing dots and dashes, indicating that there are no data for the City of London. Removing the content from particular cells can only be done for a single column, as editing happens one column at a time. So in this case, we'll have to click on every single column and remove dots and dashes step by step. To do so, we have to click on the Edit button on the cell we want to change, and then in a pop-up window, we just have to remove the content of the cell and click Apply button. From now on, our data are unified and cleaned, so now they can be converted to RDF. This process is composed of two steps, reconciliation and building a skeleton that will form a structure of the RDF graph. Now we'll focus on reconciliation, and in the next part of the movie, we'll tell you more about the second step. The main purpose of reconciliation is to connect a dataset's collection-specific vocabulary, which in our case are names of London boroughs, to an existing vocabulary on a web. Reconciliation is about giving meaning to field values, thus making our metadata interpretable. It's a good practice to reuse existing vocabulary. In our example, we use DBpedia reconciliation service because it provides two established vocabularies, curated all, and automatically generated properties. It's also available through a Sparkle endpoint. Let's go back to Google Refine and see how it should be done. In order to use a certain vocabulary, Google Refine needs to know about it. This is done by adding a reconciliation service. The reconciliation can be done against Sparkle endpoints, but also RDF dump files can be used. In our example, we'll reconcile against the DBpedia Sparkle endpoint. Please note that this step needs to be performed only once per vocabulary. We'll define a new reconciliation service the following way. From the RDF menu, select Add Reconciliation Service and then based on Sparkle endpoint. Now we have to fill this form. So, the name in our case will be DBpedia, endpoint URL dbpedia.org/sparkle, and type Virtuoso. We'll be matching our resources by RDFS label, therefore there is no need to change anything else in this form, so we just click OK. We are ready to start reconciliation process. How to do that? We use DBpedia URIs for area names column instead of coining new ones. From the area name column, we choose reconcile and then start reconciling. We select the DBpedia service that we just added. We reconcile each cell to an entity type GML feature and click Start Reconciling button. After a while, Google Refine will automatically create facets for judgment of reconciliation results, matched or not, and best candidate score. These facets have to be assessed manually now. However, when we look closer at the reconciliation results, we see that there are not many fields that were reconciled automatically, since we know that there exists an entity called London Borough of Brent. We can save a lot of time if we simply change the name of each borough to this form. However, the sentence wouldn't work for the first row. There are no London Borough of City of London. Therefore, we have to first filter our dataset and perform the name changing operation on the rest of the column. The transformation is done the following way. Click on Area Name, Edit Cells, and then choose Transform. And write the following expression. Its role is to add the London Borough of sentence to the current value of the cell, where the separator between the two joined objects is one space. We see in the preview window the result we wanted to achieve, so we click OK and start again the reconciliation process. We see now the reconciliation match is much more precise. There are only a couple of results for which the ambiguity have to be resolved. We simply click on Suggestions and choose the one which fits the best. If there are no suggestions, sometimes it's enough only to remove the last letter in the sentence and see what reconciliation service will propose to us. As you may see during the searching for match process, there are several items on the list that can be chosen. Some of the namespaces come from DBpedia and others from Yago. We suggest using only one type of namespaces, which in our case were DBpedia ones. When we finish the matching process, we are ready for creating the RDF schema skeleton. The skeleton will specify how our grid-shaped data will look like in the RDF form. The cells in each record of our data will get placed into nodes within the skeleton, but first we have to decide how the structure of our RDF data will look like. In our example, we have a dataset, Excel table, which has a label London boroughs and a structure. The structure is defined by its components, which are specified by properties. The properties represent a certain type of data, for example measure, and have a label as well, for example population density. As you see, this way we were able to describe our data in a natural language. A good practice is to use one of the existing vocabularies. Since we are working on a statistical data, we decided to work with DataCube vocabulary. This vocabulary was created to publish statistical data in a machine-friendly format to enable it to be linked and combined with related information. As we see, our data can be nicely described by DataCube vocabulary, therefore we can use it to build an RDF structure which will look more or less like that. So now we can build the skeleton in Google Refine. Go to RDF at the right top corner and click Edit RDF Skeleton. What you see here is just a basic skeleton generated by the extension. It doesn't provide a properly designed structure, that's why we delete it and start building our skeleton based on DataCube vocabulary from scratch. But first we have to update the available prefixes by clicking on plus, add prefix. We'll add DataCube vocabulary by typing QB into prefix window. If you click anywhere on a new prefix window, the URI will update automatically. Moreover, we also have to change the base URI. In our example, we decided to use example.org. At this stage, our data are not aimed at being differentiable and will be used only within a triple store. That's why such URIs are fine. Now we can start defining a skeleton. This process can be divided into two steps. First, we have to define the structure of our data and then fill it with the values from particular columns. First, we define a dataset. Click on row index URI and fill the form as shown here. For constant value, type the following URI, dataset/London boroughs, and click OK. Then add RDF type QB dataset. Our dataset is defined by its structure and label. First, we add a label to the dataset. Click Add Property and then change Property to RDFS label. We just have to provide a description for the label. Repeat this action again and this time change the property to QB structure. Now that it's enough to type structure into Search for Property window. Our structure is defined by QB structure definition, which in our case is a blank note. Since we know that DataCube vocabulary provides a proper structure for our data, that's why we simply download it from RDF extension to Google Refine website. We provided the link in the description of the movie. Now we upload it to our skeleton. In order to add it to our structure, we have to do the following. Go to Undoredo. First, we have to extract the structure we already created. Go to Extract and select all operations and select only the last RDF schema skeleton. Then copy the JSON you see in the window on the right and click Close. Paste copied JSON code in Apply window. Now we have to open the file we just downloaded and copy this piece of code to our structure. This code describes the structure of a column in a table. In this tutorial we show you how to add two columns, area name and population. The rest of them is added in a similar way, so we just show you the final skeleton in the end of this movie. Now, check in the Edit RDF Skeleton window what has changed in our structure. Please note that we added only the general structure. Now we have to change labels and column definitions to the ones that we see in our data. For example, this is how we add area name column to the skeleton. We just have to define a resource name. In our case, it will be the following URI: example.org/def/statistical dimension/area name. We also have to change the label. Moreover, area name is not of a type measure, but it's a dimension. Now we repeat that for population. Population is a measure, so we leave it. But in this case, we also have to change the resource name and label. What is more, population was defined for the year 2012, so we simply add it to the skeleton as well. So this way, we've given a structure to two columns in the table, area name and population. In order to connect a description of the table to the values for each particular columns, we have to define another tree of a type observation, which will represent the values of each column. We name it area name because we are interested in observations defining particular London boroughs. It has to be tied to the dataset. Now we have to add properties that we used to define each column in the data structure and tie them to the values in particular cells for each column. This is done in the following way. First, we do it for area name and repeat it for population. Now we have to connect the structure of the table to particular cells describing London boroughs. To do so, we create a custom expression in real language the following way. We add to London boroughs dataset URI a value from the area name cell. We repeat that for area name URI, but this time each London borough cell will be URIfied with example.org prefix. Each of these URIs will get a label too. This is just a small piece of the skeleton. You can check how the resulting RDF graph would look like by clicking on RDF preview. By using the same technique, we have to describe all columns in the table and assign proper connections between boroughs and their specifications. It takes some time, so we just show you the final outcome. First, we have to open the finished project and go to Edit RDF Skeleton. Again, by clicking on RDF Preview, we may see how our RDF looks like. At the beginning, we see the description of the table and then the values. Now we can export it to the file by clicking on RDF as turtle. Such graph can now be uploaded to a Triple Store. If you want to see how this particular project looks like, please download it from the movie description. The same process should be repeated for the two other Excel files we just downloaded, crime data and energy consumption. We just show you the final skeleton here and give you some tips about particular datasets. Since it's faster to remove unneeded columns in Excel, we did it there. For the purpose of this example, we left data for each type of crime only from the last 3 years. Moreover, we also renamed columns headers in Excel to save some post-processing time in Google Refine. For total energy consumption data, we followed exactly the same steps as in the case of crime data and London boroughs. We worked only on the newest data from 2009. This way we were able to transform statistical data to machine-friendly structured form. Moreover, such data can now be connected, but this step and the publication step will be explained in more details in the next movie.